Horsepower and torque are the two main metrics when determining how powerful an engine is. But how do engines make horsepower and torque, and how do horsepower and torque differ from each other? First of all, what is horsepower? Well, by definition, horsepower is a function of work done over an amount of time. And what is work? Work is calculated through multiplying a force by displacement. In this animation, we will look at each of these three variables, force, displacement, and time, in depth to ultimately understand the difference between horsepower and torque. Keep in mind, in this animation, we will only be looking at mechanical or imperial horsepower. Metric horsepower targets a sufficiently different audience to warrant its own animation. Now let's start by looking at the first of the two variables that make up work, torque. A great example of torque is a ratchet. What is torque? Torque is a twisting force that is a result of a force applied at a distance. If you apply a force on this ratchet at a distance, or the radius of the ratchet, you are applying a twisting force on that bolt. Let's look at an example. If you apply 15 pounds of force at a distance of 1.5 feet from the bolt, you are applying 15 times 1.5, 22.5 pound-feet of torque on that bolt. The longer the ratchet, the more torque will be applied, as you can see here. So torque is the force acting through the ratchet on the bolt, but what happens when the ratchet moves with the bolt? Well, this leads us to our second variable in our equation of work, displacement. When a force displaces or moves an object, we consider this work. A great example of work is this crate being displaced by this force pushing it. Similarly, when the torque displaces this ratchet and bolt, work is being done. Displacement in this example is measured in rotations. Now let's do a little recap. Horsepower is equal to work over time, or torque times displacement over time. Torque is a twisting force, and displacement is how far that twisting force rotates. The last variable we have to look at is time. But to explain how the time variable fits into the formula, let's jump back to the year 1782, when the inventor of horsepower, James Watt, needed a simple way to compare how much torque and power his new steam engines could produce compared to conventional horses. He needed a measure of torque in foot-pounds at a certain amount of rotations, or displacement, in a certain amount of time. While observing a horse pull on a rope running over a wheel that had a 1-foot radius that was connected to a bucket with 100 pounds of coal in it, he waited 1 minute to see how far that bucket would be displaced. After 1 minute, he discovered the 100-pound bucket was lifted 330 feet. Because the wheel doing the work had a radius of 1 foot, its circumference is 6.28 feet, meaning that to pull the weight 330 feet up, it had to rotate 52.52 times. And this is what he defined 1 horsepower as. 1 horsepower is able to pull at 100 pound-feet of torque, because the bucket was 100 pounds, through 52.52 rotations in 1 minute. Now, how would we create a formula from this? Well, you would take your torque and divide it by how much torque the horse was pulling at, 100 pound-feet, and take your rotations and divide that by how many rotations the horse was able to do in 1 minute, 52.52. And with this, you can calculate horsepower. But let's simplify this formula by not having to divide our torque by 100. All we have to do is imagine the coal was only 1 pound. But for the horse to do the same amount of work, it would have to lift that 1 pound 100 times as far. This means the coal would have to be lifted 33,000 feet, so the wheel would have to do 5,252 rotations in 1 minute. And this is how mechanical horsepower is defined. But now let's get back to that first question. How exactly do engines make torque and horsepower, and how do they differ so greatly in how much torque or horsepower they produce? Well, let's first review how an engine works. The cylinder will first suck in clean air and fuel, compress this mixture, and ignite it. This rapid expansion of the air-fuel mixture pushes the cylinder down, which I have represented by the red arrows. The spent fuel, or exhaust, is then pushed out of the cylinder and the cycle repeats itself. Now on that power stroke, the cylinder forces the connecting rod down, and the connecting rod is attached to the crankshaft at an offset. I represented this offset by these two lines, the axis of the crankshaft in blue and the offset connecting rod in red. This offset acts as a small ratchet like we saw earlier, and this is where things get interesting. The longer the connecting rod, or the longer the cylinder stroke, the longer the imaginary ratchet will be, and therefore, the more torque the engine will produce. Diesel engines require a higher compression ratio than gas, meaning a longer stroke, which results in more torque because of that longer imaginary ratchet. But these longer strokes force the cylinder to move much longer distances per stroke compared to a gasoline engine. For example, I set both of these cylinders at the same RPM, but the longer strokes of the cylinder on the left force it to move much faster to achieve the same amount of rotations per minute. This therefore increases the stresses on the engine and cuts off the maximum RPM much sooner. And this is why the design of each piston and the quantity of them in an engine is designed carefully to obtain very specific torque and horsepower curves. And this is the difference between horsepower and torque. I hope you've enjoyed this animation. If you would like to see others just like it, subscribe, and I'll see you on the next one. As always, thanks for watching.